When a beam is loaded, it bends. The beam resists the bending by developing an internal moment of resistance. We discussed this in our earlier videos. We analyzed beam sections to determine how much resisting moment they will offer at the ultimate state. We also designed the beam in such a way as to make it capable of resisting the factored bending moments acting on them. In addition to the bending moment, shear forces also act on the beam. Shear failure is catastrophic because no visible signs are shown before collapse. In this session, we will learn how to make beam sections capable of resisting the factored shear force acting on them. Shear in structural member. The section of a structural member may be subjected to the shear force due to flexure, punching, or torsion. Accordingly, the shear may be flexural shear, punching shear, or torsional shear. You may have been familiar with the relationship of moment M and shear force V in a beam, that is dm by dx equal to V. From this expression, we can say that the rate of change of the bending moment with respect to x, which is along the span, is equal to the shearing force. Thus, the shear associated with a change of bending moment along the span is known as flexural shear. Flexural shear is also commonly referred to as shear. The punching shear is a failure mechanism in structural members like slabs and foundation by shear under concentrated load. Punching shear is the possibility of punching a thin member by a concentrated load. In flat slab structures, this occurs at column support points as shown here. This failure is due to punching shear. When a member is subjected to torsion, it is subjected to torsional shear. In reinforced concrete structures, the torsional shear is usually accompanied by flexural shear. Here in this example, the loads applied to the slab surface causes twisting moment MT to act along the beam's length. These are equilibrated by the resisting torque T at the columns. In the absence of torsional moments, the structure will collapse, hence this cannot be ignored in designs. Reinforced cement concrete is a composite material, so the exact shear distribution as per elastic theory is very complex. This is shown here by the hatched portion of the curve. It is parabolic in the compression zone with 0 at the top and maximum at the neutral axis. The value of shear stress is constant in the tensile zone and is equal to the maximum shear stress Q because the concrete below the neutral axis, that is tensile zone, is assumed to be cracked and is neglected. The maximum value of shear stress Q as per elastic theory is given by Q equal to V divided by the width of the beam into lever arm. Here V is the shear force at the section while B is the width of the beam section. As per IS code 456-2000, the elastic theory approach does not represent the reinforced concrete beam's correct behavior in shear. Hence, the equation for shear stress has been simplified. IS code recommends using nominal shear stress tau V or average shear stress distribution, which is shown here and is given by tau V equal to shear force divided by BD. This formula you can also see in clause number 40.1, page number 72. Tau V, that is nominal shear stress, is merely a parameter intended to aid design and to control shear stress in reinforced concrete members. In an ordinary beam, the design shear stress or nominal shear stress is calculated as per equation given in clause number 40.1. In that equation, we need ultimate shear force Vu, B, that is width, and effective depth D only. But for a beam of varying depth, ultimate moment of resistance will also come into the picture. Let us see how this is so. Consider the simply supported beam AB of varying depth. The bottom surface of the beam makes an angle beta with the horizontal. We know that whatever type of loading, that is UDL, uniformly distributed load, concentrated load, uniformly varying load, etc., acting on the beam, for that we can calculate the factored bending moment mu and shear force Vu at any section XX on the beam. Here we have cut a section XX and we can see this factored bending moment mu and shear force Vu at this section. Here also it can be observed that with increasing moment, depth of the beam is also increasing. The beam's resistance force has been shown here. Now let us see the direction of the tensile force Tu in the steel reinforcement. For an ordinary beam, this tensile force Tu would be perfectly horizontal, but our beam, being of varying depth, the steel bars is not horizontal, and so the actual tensile force in the bar is also not horizontal. Here we can easily see that Tu will make the same angle beta with the horizontal. As Tu is not horizontal but acting at an angle, it will have a horizontal component and a vertical component, as can be seen here. Cu is the ultimate compression force developed in concrete above neutral axis. The ultimate resisting bending moment at the section Mu will be equal to Cu times lever arm Z. Since this ultimate compression force Cu has to be equal to the horizontal component of the tensile force Tu in steel reinforcement, Mu will also be equal to the horizontal component of Tu times Z, that is lever arm. Now horizontal component of Tu will be equal to the ratio of ultimate moment Mu divided by lever arm. Now this lever arm Z is measured as the distance between the ultimate compression force in concrete and the horizontal component of Tu. It can be approximately taken to be equal to D, that is the effective depth at this section. So horizontal component Tu will be now Mu by D, and the vertical component of Tu will be Mu by D tan beta, which is acting downwards. So in this case of beams with varying depth, net shear force Vu net is computed at the section, which is given as Vu net equal to the ultimate shear force minus Mu by D tan beta. So in the case of beams with varying depth, this Vu net has to be used instead of the ultimate shear force Vu to calculate the design shear stress tau V. Now we will see a beam in which the depth varies in the opposite direction, that is, depth decreases with an increase in bending moment. Here is the simply supported beam AB of varying depth. Here also the bottom surface makes an angle beta with the horizontal. We know that whatever type of loading, that is UDL, concentrated, uniformly varying load, etc., acting on the beam, for this we can calculate the factored bending moment Mu and shear force Vu at any section XX on the beam. This moment and shear force is shown here. The resistance force developed in reinforcement Tu will make the angle beta with the horizontal. Since the bottom surface of the beam is inclined at an angle beta with the horizontal, so Tu will have a horizontal component and a vertical component as shown here. Similar to the previous example, the values of the horizontal component of Tu will be Mu by D and that of vertical component of Tu will be now mu by d tan beta, which will act in upward direction. So in this case of beam with varying depth, net shear force Vu net is computed at this section will be Vu net equal to Vu plus mu by d tan beta. Well, the design shear stress tau V or nominal shear stress tau V for beams of varying depth will be Vu net divided by Dd. If we substitute Vu net value, we get this expression. This equation you can also find in clause number 40.1.1, page number 72 of IS 456-2000. Here in this formula, for an increase of depth with the increase in bending moment, we'll be using the negative sign, while for a decrease of depth with the increase of bending moment, in that case, positive sign should be used. Consider the experimental setup shown here. Here you observe the cracks pattern in the beam. To understand this pattern, let us see the effect of flexural and shear stress in beams. Here we have a simply supported beam subjected to some loading. We are interested to know the stress at this point in this section located at a distance y from the neutral axis. For this, we consider a tiny element at this point as shown. We cut the section XX which passes through this element to expose forces acting in this section. These forces are moment M and shear force V. Moment M will result in flexural, that is normal stress Fx, while the shear force V will result in shear stress tau at any point in the section. We know these stress values at any point located at a distance y from the neutral axis from the knowledge of strength of materials are given by flexural stress Fx is my by I, while shear stress tau is Vq by Ib. Here I is the second moment of area of the section about the neutral axis. Q is the first moment of area about the neutral axis of the portion of the section below the layer at a distance y from the neutral axis in this particular case. B is width of the beam at the layer at which shear stress tau is calculated. The stresses acting on this element is shown here. This combined flexural and shear stresses can be resolved into equivalent principal stresses F1 and F2 acting on orthogonal planes inclined at an angle alpha to the beam axis. The principal stresses value and angle alpha are computed using this expression. I assume you are familiar with this expression from your study on strength of material. Here F1 is tensile in nature and F2 is compressive. For different values of y, we get different values of flexural stress Fx and shear stress tau. So F1, F2 and alpha will be different. For elements located at the neutral axis, condition of pure shear stress exists. That is, tau is maximum at neutral axis and Fx is 0. So the principal stresses F1, F2 is equal to the maximum shear stress, and alpha, that is the principal plane, is inclined at an angle of 45 degrees. We can plot principal stress trajectories, which are a set of orthogonal curves whose tangent or normal at any point indicate the principal stresses directions. The dotted line shown here indicates principal tensile stress trajectories and is like a catenary curve or a suspended chain, while principal compressive stress trajectory takes the form of an arch as shown. Towards midspan, where shear stresses are low and bending dominant, the direction of principal stresses tends to be parallel to the beam axis. Near the supports, where the shearing forces are greater, the principal stresses become inclined and greater the shear force, greater is the inclination. For potential crack patterns, it must be noted that cracks would develop in a direction that is perpendicular to that of the principal tensile stresses. Here in this beam, without any shear reinforcement, you may observe several fine cracks, but the beam's final failure is due to diagonal tension crack. The provision of shear reinforcement can avoid this failure. Let us discuss now shear reinforcement in beams. The shear failure is caused by diagonal tension with cracks running at 45 degrees to the beam axis. So, we must provide some kind of steel reinforcement to prevent the separation of the concrete along the crack. In other words, we must provide steel reinforcement to keep the two parts together. This is called shear reinforcement, and it can be provided either in the form of vertical stirrups, inclined stirrups, or bent up bar along with stirrups. The primary function of stirrups are to resist a part of shear, to resist the growth of the inclined cracks and improve aggregate interlock, and to tie the longitudinal bars in place, thereby increase the dowel action. When the shear reinforcements are provided vertically, they are called vertical stirrups or simply stirrups. They are formed by bending steel bars around the tensile reinforcement bars as shown in here. It is necessary to provide additional small diameter bars, usually 12 mm dia, in the beam's compression zone to anchor the stirrups properly. These bars are known as stirrup holder or stirrup suspenders. For a doubly reinforced beam, these bars in the compression zone will be already present, so there is no need to provide additional bars. These vertical stirrups should be provided throughout the length of the beam at suitable spacing. This spacing is determined while we design the stirrups. Here, the stirrups have two legs. Such stirrups are called two-legged stirrups. In some cases, to resist more significant shear stresses, it becomes necessary to provide several legged stirrups such as four-legged, six-legged, etc. It is desirable to locate the hooks of the closed stirrups in the compression zone. In this way, the ends of the stirrups bar will be under confinement. This is necessary for improved anchorage and to avoid crack initiation and opening of hooks of stirrups. Another point to note is that the hooks of alternate stirrups should be on opposite sides as shown in this animation. The inclined stirrups should be placed in such a way that they intercept the cracks nearly at right angles. Such an arrangement will resist the widening and propagation of the cracks. These stirrups are usually inclined at 45 degrees with the main bars of the beam. An angle of less than 45 degree is not recommended because they may slip along the beam's longitudinal bars. Inclined stirrups are most effective in reducing the width of the inclined cracks. For example, in cases where beams are subjected to high axial tensile force, there will be the formation of transverse cracks which will extend to the full depth of the beam. Also, such cracks will be perpendicular to the beam axis. So, the inclined stirrups will effectively intercept those cracks. But in the case of beams subjected to seismic loads, the shear force's direction may get reversed. In such beams, the inclined stirrups will be entirely ineffective as these stirrups will not intercept the crack now. Shear reinforcement using bent-up bars is provided by bending up one or two main bars. Here, the bent-up bar is shown separately from the main tensile steel only for clarity. The vertical distance between the bottommost surface of the bent-up bar and that of the other main tensile steel is shown to be 0 mm. It indicates that both these bars is along the same layer. Just as in the case of inclined stirrups, the direction of bent up should be in such a way that they intercept the crack nearly at right angles. We have to consider another point while using bent up bars for shear reinforcement. That is, the design should not be in such a way that all design shear load is resisted by the bent up bar alone. We must provide stirrups also. Clause number 40.4 of IS 456-2000 specifies that where bent up bars are provided, their contribution towards shear resistance shall not be more than half that of the total shear reinforcement. For example, if a factored shear force of 50 kN has to be resisted at a section, all the bent up bars at the section together should provide a resistance of 25 kN only. If the bent up bars given is capable of giving a resistance greater than 25 kN, the stirrups provided at the section should also be capable of giving resistance equal to or greater than 25 kN.